Okay, dear students, I think you have understood the things we discussed in last class. We discussed that any spontaneous process, taking the example of the irreversible flow of heat, with that phenomenological model, we established that the ds prod is greater than 0 when the process is irreversible. That is, for irreversible flow of heat, the entropy production always increases, entropy is always produced. Okay, so in the similar line, today we take another phenomenological model, and here we show that the entropy always increases when there is a material flow from a region of higher chemical potential to a region of lower chemical potential. And to start with, we consider this model where we place, there are two compartments which is together, these two compartments are placed within a rigid adiabatic wall, that is, no heat can come out, no material can flow from outside of these two compartments. And in between this compartment 1 and this compartment 2, and in compartment 1, in between the compartments, the wall is diathermal, flexible and permeable. Okay, and here in compartment 1, the components are P1, V1, T1, S1, mu1, N1, that is pressure, volume, temperature, entropy, chemical potential and number of moles, and the same in the compartment 2 is P2, V2, T2, S2, mu2 and N2. So here a little description about the model. In this diagram, each of the two components is in equilibrium individually, but the two compartments are not in equilibrium with each other, so that material or heat can flow from this compartment to this compartment or this compartment to this compartment. And the wall is diathermal, so it allows the heat to flow, flexible, so the volume can change, and permeable, so the matter can flow. So two compartments are separated by a diathermal, heat conducting, flexible and permeable wall. Therefore, the energy as heat, matter can flow through the volume, and matter can flow through, and also the volume of individual compartments may change as the wall is flexible. So each compartment must be large enough, so that, let us imagine these two compartments are very large, such that the transport of heat and matter from one compartment to another do not appreciably disturb the equilibrium state of each compartment. So that though the matter is flowing, but the change is negligible if two compartments are very large. In that case, individual compartments, the components in the individual compartments remain almost constant, even if little change occurs through the flexible membrane. So now in the whole model, the total entropy of the two component system is S, which is S1 for compartment 1 and S2 for compartment 2, where S1 is a function of U1, V1 and N1, and S2 is a function of U2, V2 and N2. So in general, F is a function of UVN, that is internal energy, volume and number of moles, such that ds equal to del S del U with constant Vn and du plus del S del V with constant U and N dV plus del S by del N with constant U and V into dN. So now look at here. So for a closed system, dq equal to du plus pdv, or du equal to TdS, dq is replaced by TdS minus PdV, but for open system, du equal to TdS minus PdV plus mu dN. As these systems are open individually, these compartments are open, the matter can flow through from one compartment to another. So here the formalism is made on the basis of open system. So now at keeping V and N constant, so that del S by del U, so del S by del U at constant V and N, so that these two things become 0, and this del S by del U Vn becomes T by 1 by T. Similarly, del S by del V, so del S by del V at constant U and N becomes P by T, and del S by del N at constant U and V becomes minus mu by T. So now we substitute these three things over here, and we find that du, this becomes du by T plus pdv by T minus mu dN by T. So for individual components, the compartments S1, for compartment number 1, S1 becomes du1 by T1, plus P dV1 P1 dV1 by T1 minus mu1 dN1 by T1, and for compartment 2 this is dU2 by T2 plus P2 dV2 by T2 minus mu2 dN2 by T2. So as in this model there is no heat exchange with the surroundings or anything, they are adiabatic jacket, so ds exchange will be 0. So the whole entropy change, that is ds1 plus ds2, together it will be only ds prod. So ds prod equal to ds1 plus ds2. So now we add ds1 and ds2. So this is ds1, this is ds2, so that we add ds1 and ds2, that becomes du1 by t1 plus du2 by t2 plus p1 dv1 by t1 plus p2 dv2 by t2 minus mu1 dn1 by t1 minus mu2 dn2 by t2, that should be greater than equal to 0. The greater than sign will hold good for irreversible processes and equal to sign will hold good for reversible process. Okay, now we come to the next part of the discussion. As the two compartment system is isolated and rigid, so that u1 plus u2 equal to constant, that is du1 equal to minus du2. Once again, the outside jacket is rigid, so v1 plus v2 equal to constant, so that dv1 equal to minus dv2. And once again, n1 plus n2 is constant as matter is not going out of the two compartment system, so dn1 equal to minus dn2. So now putting these three things in the previous equation, we get ds prod equal to dE1 into 1 by T1 minus 1 by T2 plus dV1 into P1 by T1 minus P2 by T2 minus dN1 into mu1 T1 minus mu2 by T2, that should be greater than equal to 0. So the first term in the above equation is exactly the same as we discussed in the last class in connection with the irreversible flow of heat. If you recall, this first term is nothing but that we discussed in connection with the irreversible flow of heat. So we know that this part will contribute due to the exchange of heat energy between two components. So we are not going to discuss it further here. Now let us look at closely at the second term. If you put T1 equal to T2, that means if the temperature is constant in same in both the compartments, T1 let T1 equal to T2 equal to T, and the chemical potential in compartment 1 and 2 are same, that is mu1 equal to mu2, then you get putting these things over here in this equation, what you get? We get T ds prod equal to these term survives, so dv1 minus P1 by P2, that is should be greater than equal to 0. So now what does it mean? Which means that dv1 is greater than 0 if P1 is greater than P2. That is the flexible wall will move towards right. On the other hand, if dv1 is less than 0, dv1 will be less than 0 if P1 is less than P2, which is rather expected. That means when pressure P1 is higher than P2, then volume of compartment 1 will change to the with the positive, it will increase, so dv1 will be higher positive, and if pressure P2 is more than P1, then dv1 will be negative, because in that case dv2 will be positive. So that is also a kind of common sense that with pressure the volume increases, and that is the contribution due to that to the total S prod. Now the third term, which is more interesting and in connection with the discussion we proposed, that is the third term has to do with the material flow or diffusion. If we take T1 equal to T2 equal to T1, that means it's isothermal, and P1 equal to P2, so isobaric, the pressures are same, then what it becomes? This equation becomes the above equation. This equation becomes Ts prod equal to minus dN1 into mu1 minus mu2, that should be greater than equal to 0, which indicates that dN1 is less than 0 if mu1 is greater than mu2. If mu1 is greater than mu2, then this thing must be negative, then negative minus sign, the overall thing becomes positive. This means that matter will flow from compartment 1 to compartment 2 if the concentration of the diffusing species is greater in compartment 1 than compartment 2. Okay, because concentration is logarithmically proportional with the mu is logarithmically proportional with the concentration. So as the concentration increases, the chemical potential increases. So with the increase in the chemical potential of compartment 1, the matter will flow from compartment 1 to compartment 2. So in that case, this thing will be positive and this dN1 must be negative, because the number of moles will reduce in compartment 1. But overall, that's also a common experience. So, but in overall, whatever we do, the TdS prod becomes greater than 0. So, if the concentration in turn the chemical potential in compartment 1 is higher than that in compartment 2, the material will flow from compartment 1 to compartment 2. As a result, dN1, that means the number of moles in compartment 1 will decrease and TdS prod will be greater than 0 for irreversible process, and it should be equal to 0 for reversible process. And on the other hand, the opposite will happen. If mu2 is greater than mu1, then this thing will be negative. So dN1 must be positive, because then there will be gain in the number of moles by compartment 1. As a result, the overall TdS prod will be positive, because this is negative, this is negative. Overall, it becomes positive for irreversible process. So overall, whatever we do, the TdS prod becomes greater than equal to 0, where greater than is for irreversible process and equal to sign holds good for reversible process. So with these two examples, the example in the last class with the irreversible flow of heat, we saw that ds prod is greater than 0 for irreversible process, and here we see that TdS prod is greater than 0 for irreversible process. T is always positive, so ds prod is greater than 0. So that means ds prod being greater than 0 is a fundamental requirement in any irreversible process. So to consider the irreversibility or the extent of irreversibility of a process, we don't need to consider the whole entropy, rather a part of it which is known as ds prod. So that part we can look upon to ascertain the irreversibility of a process. That means the fundamental quantity ds prod or s prod is, that means the quantity s prod is fundamental in connection with any irreversible process. Okay, so today we end the discussion here. So I hope you will understand, and you will get back if you have any query. So once you understand that, we will proceed for the next part of the discussion. Thank you very much.